Horsepower is unit of measurement of power, the rate at which work is done. The most common conversion factor, especially for electrical power, is 1 HP equals 746 watts. The term was adopted in the late 18th century by Scottish engineer James Watt to compare the output of steam engines with the power of draft horses. It was later expanded to include the output power of other types of piston engines, as well as turbines, electric motors and other machinery. The definition of the unit varied between geographical regions. Most countries now use the SI unit watt for measurement of power. With the implementation of the EU Directive 80/EEC on January 1, 2010, the use of horsepower in the EU is only permitted as supplementary unit. Definitions of term units called horsepower have differing definitions. The mechanical horsepower, also known as imperial horsepower, of exactly 550 foot-pounds per second is approximately equivalent to 745.7 watts. The metric horsepower of 75 a kilogram force m per second is approximately equivalent to 735.5 watts. The Fdeste currency RKEPS is a name for a group of similar power measurements used in Germany around the end of the 19th century, all of about 1 metric horsepower in size. The boiler horsepower is used for rating steam boilers and is equivalent to 34.5 pounds of water evaporated per hour at 212 degrees Fahrenheit, or 9,809.5 watts. 1 horsepower for rating electric motors is equal to 746 watts. Continental European electric motors used to have dual ratings, using a conversion rate of 0.735 a kilowatt for 1 HP. British Royal Automobile Club horsepower is one of the tax horsepower systems adopted around Europe which make an estimate based on several engine dimensions. History of the unit. The development of the steam engine provided a reason to compare the output of horses with that of the engines that could replace them. In 1702, Thomas Savery wrote in The Miner's Friend, "So that an engine which will raise as much water as 2 horses, working together at one time in such a work, can do, and for which there must be constantly kept 10 or 12 horses for doing the same. Then I say, such an engine may be made large enough to do the work required in employing 8, 10, 15, or 20 horses to be constantly maintained and kept for doing such a work." The idea was later used by James Watt to help market his improved steam engine. He had previously agreed to take royalties of 1/3 of the savings in coal from the older Newcomen steam engines. This royalty scheme did not work with customers who did not have existing steam engines but used horses instead. Watt defined 1 horsepower as the amount of power required from a horse to pull 150 pounds out of a hole that was 220 feet deep in 1 minute. Watt's calculated the kinetic energy is 33,000 feet lb per minute. The fact that 1 horsepower is the power to lift 1 ton 1 rod in 1 minute should also be noted. 2 horses together produced over 30 HP. Watt determined that a horse could turn a mill wheel 144 times in an hour. The wheel was 12 feet in radius. Therefore, the horse traveled 2.4 a, 12 feet in 1 minute. Watt judged that the horse could pull with a force of 180 pounds. So, this was rounded to an even 33,000 FTA pound force per minute. Watt determined that a pony could lift an average 220 a pound force 100 ft per minute over a 4-hour working shift. Watt then judged a horse was 50% more powerful than a pony and thus arrived at the 33,000 FTA pound force per minute figure. Engineering in history recounts that John Smeaton initially estimated that a horse could produce 22,916 foot-pounds per minute. John Desaguliers had previously suggested 44,000 foot-pounds per minute and Treadgold 27,500 foot-pounds per minute. Watt found by experiment in 1782 that a brewery horse could produce 32,400 foot-pounds per minute. James Watt and Matthew Boulton standardized that figure at 33,000 the next year. Most observers familiar with horses and their capabilities estimate that Watt was either a bit optimistic or intended to underpromise and overdeliver. Few horses can maintain that effort for long. Regardless, comparison with a horse proved to be an enduring marketing tool. In 1993, R.D. Stevenson and R.J. Wassersug published an article calculating the upper limit to an animal's power output. The peak power over a few seconds has been measured to be as high as 14.9 HP. However, Stevenson and Wassersug observe that for sustained activity, a work rate of about 1 HP per horse is consistent with agricultural advice from both 19th and 20th century sources. When considering human-powered equipment, a healthy human can produce about 1.2 HP briefly and sustain about 0.1 HP indefinitely. Trained athletes can manage up to about 2.5 HP briefly and 0.3 HP for a period of several hours. Calculating power. If torque and angular speed are known, using a coherent system of units, the power may be calculated using the relationship. Where is power, is torque, and is angular speed. When using other units or if the speed is in revolutions per unit time rather than radians, a conversion factor has to be included. When torque is in pound-foot units, rotational speed is in rpm and power is required in horsepower. The constant 5252 is the rounded value of ref. When torque is in inch-pounds. The constant 63,025 is the rounded value of a rev. Current definitions. The following definitions have been widely used. In certain situations it is necessary to distinguish between the various definitions of horsepower and thus a suffix is added, HP, I, for mechanical horsepower, HP, M, for metric horsepower, HP, S, for boiler horsepower and HP, E, for electrical horsepower. Hydraulic horsepower is equivalent to mechanical horsepower. The formula given above is for conversion to mechanical horsepower from the factors acting on a hydraulic system. Mechanical horsepower, assuming the third CGPM definition of standard gravity, Gn equals 9.806665 ams2, is used to define the pound force as well as the kilogram force, and the international avoirdupois pound. 1 mechanical horsepower is. Or given that 1 HP equals 550 FTA pound force per second, 1 FT equals 0.3048 am, 1 lbfa per mil 4.448 n, 1 J equals 1 Nm, 1 W equals 1 JS, 1 HP equals 746 W, metric horsepower. The various units used to indicate this definition all translate to horsepower in English, so it is common to see these values referred to as horsepower or HP in the press. Releases or media coverage of the German, French, Italian, and Japanese automobile companies. British manufacturers often intermix metric horsepower and mechanical horsepower depending on the origin of the engine in question. Sometimes the metric horsepower rating of an engine is conservative enough so that the same figure can be used for both ATEEC with metric HP and SAEJ 1349 with imperial HP. DIN 66036 defines 1 metric horsepower as the power to raise a mass of 75 kilograms against the Earth's gravitational force over a distance of 1 meter in 1 second. This is equivalent to 735.49875 a W or 98.6% of an imperial mechanical horsepower. In 1972, the PS was rendered obsolete by EEC directives, when it was replaced by the kilowatt as the official power measuring unit. It is still in use for commercial and advertising purposes, in addition to the kilowatt rating, as many customers are still not familiar with the use of kilowatts for engines. Other names for the metric horsepower are the Dutch paardenkracht, the French cheval, the Portuguese cavalo, the Russian TH 3/4 nth degree TH 1/2 TH degree NN TH degree, the Swedish Harkurensistkraft, the Finnish Havosvoima, the Norwegian and Danish Hestekraft, the Hungarian La Kudera, the Czech Koskazala and Slovak Kunska Sila, the Bosnian Serbian Konjka Snaga, the Bulgarian THSH TH 3/4 TH 1/2 NTH degree NTH degree, the Macedonian THSH TH 3/4 NSH NTH degree NTH degree. The Polish Komachanici, Slovenian Konjka and the Romanian Kalfuta, which all equal the German Fdesta currency RKE. In the 19th century, The French had their own unit, which they used instead of the CV or horsepower. It was called the poncelet and was abbreviated P. French and Italian tax horsepower. In addition, the capital form CV is used in Italy and France as a unit for tax horsepower, short for, respectively, cavalier vapeur and chevaux vapeur. CV is a non-linear rating of a motor vehicle for tax purposes. The Cove rating, or fiscal power, is, where P is the maximum power in kilowatts and U is the amount of carbon dioxide emitted in grams per kilometer. The term for CO2 measurements has been included in the definition only since 1998, so older ratings in CV are not directly comparable. The fiscal power has found its way into naming of automobile models, such as the popular Citroën N2 Chevaux. The Cheval Vapeur unit should not be confused with the French Cheval Fiscal. Electrical horsepower. The horsepower used for electrical machines is defined as exactly 746 AW. The nameplates on electrical motors show their power output, not their power input. Outside the United States, watts are generally used for electrical power applications. Drawbar horsepower. See also power at rail. Drawbar horsepower is the power a railway locomotive has available to haul a train or an agricultural tractor to pull an implement. This is a measured figure rather than a calculated one. A special railway car called a dynamometer car coupled behind the locomotive keeps a continuous record of the drawbar pull exerted, and the speed. From these, the power generated can be calculated. To determine the maximum power available, a controllable load is required. It is normally a second locomotive with its brakes applied, in addition to a static load. If the drawbar force is measured in pounds force and speed is measured in miles per hour, then the drawbar power in horsepower is. Example, how much power is needed to pull a drawbar load of 2,025 pounds force at 5 miles per hour? The constant 375 is because 1 HP equals 375 lb/F mile per hour. If other units are used, the constant is different. When using a coherent system of units, such as SI, no constant is needed, and the formula becomes RAC horsepower. This measure was instituted by the Royal Automobile Club in Britain and was used to denote the power of early 20th century British cars. Many cars took their names from this figure, while others had names such as 40/50 horsepower, which indicated the RAC figure followed by the true measured power. Taxable horsepower does not reflect developed horsepower. Rather, it is a calculated figure based on the engine's bore size, number of cylinders, and a presumption of engine efficiency. As new engines were designed with ever-increasing efficiency, it was no longer a useful measure, but was kept in use by UK regulations which used the rating for tax purposes. Where D is the diameter of the cylinder in inches, N is the number of cylinders, this is equal to the engine displacement in cubic inches divided by 10 euro then divided again by the stroke in inches. Since taxable horsepower was computed based on born number of cylinders, not based on actual displacement, it gave rise to engines with under-square dimensions. This tended to impose an artificially low limit on rotational speed, hampering the potential power output and efficiency of the engine. The situation persisted for several generations of 4- and 6-cylinder British engines, for example, Jaguar's 3.4-litre XK engine of the 1950s had 6 cylinders with a bore of 83 ohm and a stroke of 106 ohm, where most American automakers had long since moved to over-square V8s. Measurement. The power of an engine may be measured or estimated at several points in the transmission of the power from its generation to its application. A number of names are used for the power developed at various stages in this process, but none is a clear indicator of either the measurement system or definition used. In the case of an engine dynamometer, power is measured at the engine's flywheel. With a chassis dynamometer or rolling road, power output is measured at the driving wheels. This accounts for the significant power loss through the drivetrain. In general, nominal is derived from the size of the engine and the piston speed and is only accurate at a pressure of 48 kPa. Indicated or gross horsepower, plan/33,000, minus frictional losses within the engine, equals. Brake/net/crankshaft horsepower, minus frictional losses in the transmission, equals shaft horsepower, minus frictional losses in the universal joint S, differential, wheel bearings, tire and chain equals effective, true or commonly referred to as wheel horsepower. All the above assumes that no power inflation factors have been applied to any of the readings. Engine designers use expressions other than horsepower to denote objective targets or performance, such as brake mean effective pressure. This is a coefficient of theoretical brake horsepower and cylinder pressures during combustion. Nominal horsepower. Nominal horsepower is an early 19th century rule of thumb used to estimate the power of steam engines. NHP equals 7x area of piston x equivalent piston speed / 33,000. For paddle ships the piston speed was estimated as 129.7 x 1 / 3.35. The stroke was the distance moved by the piston. For the nominal horsepower to equal the actual power, it would be necessary for the mean steam pressure in the cylinder during the stroke to be 48 kPa and for the piston speed to be of the order of 54 €75 meter per minute. The French Navy used the same definition of nominal horsepower as Britain. Indicated horsepower. Indicated horsepower is the theoretical power of a reciprocating engine if it is completely frictionless and converting the expanding gas energy in the cylinders. It is calculated from the pressures developed in the cylinders, measured by a device called an engine indicator hence indicated horsepower. As the piston advances throughout our stroke, the pressure against the piston generally decreases, and the indicator device usually generates a graph of pressure versus stroke within the working cylinder. From this graph the amount of work performed during the piston stroke may be calculated. Indicated horsepower was a better measure of engine power than nominal horsepower because it took account of steam pressure. But unlike later measures such as shaft horsepower and brake horsepower, it did not take account of power losses due to transmission and gearboxes. Brake horsepower. Brake horsepower is the measure of an engine's horsepower before the loss in power caused by the gearbox and drivetrain. In Europe the DIN standard tested the engine fitted with all ancillaries and exhaust system as used in the car. The American SAE system tests without alternator, water pump, and other auxiliary components such as power steering pump, muffled exhaust system, etc. so the figures are higher than the European figures for the same engine. Brake refers to the device which was used to load an engine and hold it at a desired rotational speed. During testing, the output torque and rotational speed were measured to determine the brake horsepower. Horsepower was originally measured and calculated by use of the indicator, and later by means of a Deprony brake connected to the engine's output shaft. More recently, an electrical brake dynamometer is used instead of a Deprony brake. Although the output delivered to the driving wheels is less than that obtainable at the engine's crankshaft, a chassis dynamometer gives an indication of an engine's real-world horsepower after losses in the drivetrain and gearbox. Shaft horsepower. Shaft horsepower is the power delivered to the propeller shafts of a steamship, or an aircraft powered by a piston engine or a gas turbine engine, and the rotors of a helicopter. This shaft horsepower can be measured with instruments, or estimated from the indicated horsepower and a standard figure for the losses in the transmission. This measure is not commonly used in the automobile industry, because in that context drivetrain losses can become significant. Engine power test codes. Engine power test codes determine how the power and torque of an automobile engine is measured and corrected. Correction factors are used to adjust power and torque measurements to standard atmospheric conditions to provide a more accurate comparison between engines as they are affected by the pressure, humidity, and temperature of ambient air. There exist several standards for this purpose, some described below. Society of Automotive Engineers SAE International, Sae Gross Power. Prior to the 1972 model year, American automakers rated and advertised their engines in brake horsepower, frequently referred to as Sae Gross Horsepower, because it was measured in accord with the protocols defined in SAE standards J245 and J1995. As with other brake horsepower test protocols, Sae Gross HP was measured using a stock test engine, generally running with few belt-driven accessories and sometimes fitted with long tube test headers in lieu of the OEM exhaust manifolds. The atmospheric correction standards for barometric pressure, humidity and temperature for testing were relatively idealistic. Sae Net Power. In the United States, the term BHP fell into disuse in 1971 Euro 72, as automakers began to quote power in terms of Sae Net Horsepower in accord with SAE standard J1349. Like Sae Gross and other brake horsepower protocols, Sae Net HP is measured at the engine's crankshaft, and so does not account for transmission losses. However, the Sae Net Power testing protocol calls for standard production-type belt-driven accessories, air cleaner, emission controls, exhaust system, and other power-consuming accessories. This produces ratings in closer alignment with the power produced by the engine as it is actually configured and sold. Sae Certified Power. In 2005, the SAE introduced Sae Certified Power with SAE J2723. This test is voluntary and is in itself not a separate engine test code but a certification of either J1349 or J1995, after which the manufacturer is allowed to advertise certified to SAE J1349, or certified to SAE J1995 depending on which test standard have been followed. To attain certification, the test must follow the SAE standard in question, take place in an ISO 9000/9002 certified facility and be witnessed by an SAE-approved third party. A few manufacturers such as Honda and Toyota switched to the new ratings immediately, with multi-directional results. The rated output of Cadillac's supercharged Northstar V8 jumped from 440 to 469 HP under the new tests, while the rating for Toyota's Camry 3.0 L1MZ FE V6 fell from 210 to 190 HP. The company's Lexus ES330 and Camry SE V6 were previously rated at 225 HP, but the ES330 dropped to 218 HP while the Camry declined to 210 HP. The first engine certified under the new program was the 7.0 LLS7 used in the 2006 Chevrolet Corvette Z06. Certified power rose slightly from 500 to 505 HP. While Toyota and Honda are retesting their entire vehicle lineups, other automakers generally are retesting only those with updated powertrains. For example, the 2006 Ford 500 is rated at 203 horsepower, the same as that of 2005 model. However, the 2006 rating does not reflect the new SAE testing procedure, as Ford is not going to spend the extra expense of retesting its existing engines. Over time, most automakers are expected to comply with the new guidelines. SAE tightened its horsepower rules to eliminate the opportunity for engine manufacturers to manipulate factors affecting performance such as how much oil was in the crankcase, engine control system calibration, and whether an engine was tested with premium fuel. In some cases, such can add up to a change in horsepower ratings. A road test editor at Edmunds.com, John D. Petro, said decreases in horsepower ratings for some 06 models are not that dramatic. For vehicles like a mid-size family sedan, it is likely that the reputation of the manufacturer will be more important. Deutsches Institut für Verkehrsnormung 70020, DIN 70020 is a standard from German DIN regarding road vehicles. DIN testing, unlike SAE, tested the engine as installed in the vehicle, with cooling system, charging system and stock exhaust system all connected. Because the German word for horsepower is Feste Currency RKE, in Germany it is commonly abbreviated to PS. DIN HP is measured at the engine's output shaft, and is usually expressed in metric rather than mechanical horsepower. Economic Commission for Europe R24, ECE 24 is a UN standard for the approval of compression ignition engine emissions, installation and measurement of engine power. It is similar to DIN 70020 standard, but with different requirements for connecting an engine's fan during testing, causing it to absorb less power from the engine. Economic Commission for Europe R85, ECER 85 is a UN standard for the approval of internal combustion engines with regard to the measurement of the net power. 80 EEC of December 16, 1980 is a European Union standard for road vehicle engine power. International Organization for Standardization, ISO 14396 specifies the additional method requirement for determining the power of reciprocating internal combustion engines when presented for an ISO 8178 exhaust emission test. It applies to reciprocating internal combustion engines for land, rail and marine use excluding engines of motor vehicles primarily designed for road use. ISO 1585 is an engine net power test code intended for road vehicles. ISO 2534 is an engine gross power test code intended for road vehicles. ISO 4164 is an engine net power test code intended for mopeds. ISO 4106 is an engine net power test code intended for motorcycles. ISO 9249 is an engine net power test code intended for earth-moving machines. Japanese Industrial Standard D1001, JIS D1001 is a Japanese net and gross engine power test code for automobiles or trucks having a spark ignition, diesel engine, or fuel injection engine. See also, brake-specific fuel consumption Euro, how much fuel an engine consumes per unit energy output, European Units of Measurement Directives, horsepower hour, torque, references. External links, How Stuff Works, Horsepower.